Hello and welcome back. We're taking another look at some of these asymptotic notation proofs. And now we're going to start to explore little o and little omega. So first, let's just take a look here at little o. Notice that little o is right. Not sure what's going on there. I don't like that I can't see that pen. Normally, I wonder if we like close this and reopen it, if perhaps then we will be able to see it. There we go. Okay, that was just driving me crazy. So let's start with the definition right here of little o, and we'll see that something is in little o if and only if for all values of m greater than 0, there's going to exist an n naught for all values of n greater than n naught, where this inequality holds true. Now, the only thing that is different between this and big O is this right here. In big O, we get to set that multiple of g of n and give ourselves that upper bound. We can just say there definitely exists an upper bound where this is going to work for all n greater than the n naught that we give. Now here, what we're basically saying is it doesn't matter what m is, this should hold true. This entire inequality should hold true, regardless if m is 0.01 or m is 1 million or m is 1 bazillion. And so effectively what we're saying is that it's analogous to the function of f of n being strictly less than the function of g of n, because the takeaway is that the m value can't affect it. Now, it's not enough to just look at this, because given the official definition, when we do our selection right here for n naught, we're going to need to select it most likely in terms of m. So we can't just let m just not, like, we can't just only look at this. We do have to remember that we may need to use the fact that m exists to prove our point, but to wrap our brains around it, we're basically just saying that there's no value of m that would affect the inequality. So f of n is always going to be strictly less than g of n. Little omega is exactly the same as in this scenario, but it matches up with big omega. So we see the same quantifiers as little o, where the only difference is that this is now that for all, and then this is exactly the same as big omega was, except again, because of that for all, it's like saying we don't care about that m. It doesn't matter what that m is. It should not ever break this inequality if this inequality is true. So it is sort of analogous to saying f of n is strictly greater than g of n. And so we're going to look at a couple of proofs in the next couple of videos, which will address this. Okay, so let's get started. So let's start by looking at this one here, where we're saying n to the 7 plus 8n to the 6 is going to be in little omega of n to the 5 plus 1. So what this is saying is that for all m greater than 0, there exists an n naught greater than 0 for all n greater than n naught, where f of n is going to be less than or equal, oh no, it's a omega, so greater than or equal to m times g of n. So if we write this out with the actual information, that's like saying n to the 7 plus 8n to the 6 is going to be greater than or equal to m times n to the 5 plus 1. And again, we have no control over what that m value is. M greater than 0 is arbitrary. So the only thing that we have access to is trying to figure out what we want to set that lower value of n to. What should we let n not equal so that we can set that lower bound on the rest of the n's? So the very first thing that we can do is deal with the fact that we once again have a difference in terms. And so we can factor stuff out to try and get a better understanding of what this problem requires. So if we take that n to the 7 plus 8n to the 6, we factor out that n to the 7. No. Yes. Greater than or equal. I don't know why I thought I was going to take that side when we always take the side with the M. Formula. Come on, Lauren, don't reinvent the wheel. So here is the side that we need to hit a factored, pardon me, hit a factored form with. So we'll factor out that n to the 5, and we're going to get 1 plus 1 over n to the 5 right here. Okay, awesome. And so now that we have this value here, we can take a look at that term, that 1 over n to the 1 over n to the 5 and 1 over n to the 5 and determine what we can glean about this. What here could help us find the value that we're looking for. So a reminder what we're trying to work toward on the other side is really going to help us be able to understand how to go about solving this problem. On the other side, with that n to the 7 plus 8n to the 6, we know already that n to the 5 is going to be less than that for all of these values. So what can we do with this 1 over n to the 5 to help us? Let's start over. Let's start out by factoring out that n to the 5 and see what we can learn about this problem space. 1 plus 1 over n to the 5 is going to be like that. Pardon me. Now, dealing with all of these half numbers and such is so difficult. We don't want them. If we can prove that this right here is going to, if n is going to be greater than 1, that this entire thing will definitely be less than 2. So that allows us to come up with that intermediate term that we want to stick right between. So if we say that we know that n is going to be greater than 1, we'll be able to say something like, this term right here is definitely going to be less than m times n to the 5 times 2. Which is going to help us because having those whole numbers is always much nicer. So then we can address the right-hand side or the left-hand side where we had that 7. We basically now have something that looks like this, where this is greater than this, which is greater than what we originally had of this. We've already proven that this is true when n is greater than 1. So now we're going to look at this side and see what we can figure out. Well, let's isolate n in terms of m as we have been doing. So we have this n to the 7 plus 8n to the 6, which is less than 2 to the m times n to the 5. So if, oops, sorry, I don't know why it keeps doing that. If we give our n value something that will be greater than 2 to the m, what we'll be able to say then is we can use our round up trick. And we'll be able to say that 2 to the m times n to the 5, so I'm just rewriting this right over here, is going to be less than, because of this, we know that n is going to be strictly greater than that value, n to the 6. That's what we get to be able to say. We get to use that trick. And since we previously decided that n was going to be greater than 1, we could round up again. We could say that we know that n to the 7 plus 8n to the 6 will be greater than n to the 6 alone, because we're not dealing in that 0 to 1 space. So there's no reason for this not to be greater than this, right? We know n to the 7 will be greater than n to the 6. We know that 8n to the 6 is clearly greater than just n to the 6 alone. Therefore, adding those two together will keep us above n to the 6. So what we've then proven is we've said that if we let n equal, so n had to be greater than 0, but a reminder, of course, that we need to frame it in terms of n naught, a max between n naught plus 1, and our other value was that 2m plus 1, we're able to observe that n is strictly greater than the max between n naught plus 1 and 2m. And then at this point, we'll be able to say that since we know that n is going to be greater than n naught plus 1, we're able to say things like we know that this entire term is strictly less than this term right here. And then when we see this other side here, when we say we know that n is going to be greater than 2 to the m as well, it's both going to be greater than 1 at a minimum and greater than 2 to the m at a minimum. We're able to look at this side and use our round up tricks to prove that this is going to be greater than this, and this is going to be greater than this. Therefore, this is going to be greater than our original this. And therefore, we end up with that whole proof as needed. And that's complete. So I know that I have been showing like the nicely written out proof because that is, of course, in our notes. We don't need me to show that. I guess what I could do just very quickly in case you forget where that is show right here. This one? Is that the one we're looking at? I think it is. I think that's the one that we just looked at. Let me just move this out of the way. That right here, we can see how we would want to frame it in like our official proof language. So we give that m being greater than 0 as an arbitrary value, and that we're going to know that we're aware that we can only really mess with that n naught. So we're constructing an n naught for all n greater than n naught. So we're going to let our n naught value, oh, did I say n? Oh my gosh. We're going to let our n naught value be this max. So then that way we can say that we observe that our n is going to be greater than that scenario. I'll fix that before we head back over. It's a good thing that we're doing this. So then we're able to actually see that those two pieces are true, which allowed us to imply the things that we implied. And there is the final work all the way through. Now, I will just quickly go back here and rectify that, where I did say that we needed this to be in terms of n naught, and then I continued to not fix that. So we're going to say let n naught equal that maximum. And we don't need that plus 1 anymore, because now we're just saying that n is going to be greater than that maximum since n is greater than n naught. Sorry about that. There we go. And so now we can see both how the intuition behind getting those values for n naught sort of occurred, and we can see how to structure it nicely given our official notes as well. Okay, so that's this whole question. We're going to go ahead and wrap that one up, and then we're going to move on to the next exercise, exercise 5, where we will delve into another example of a not in the set of, but in this case, it will be for little o. Thanks, everybody, and have a great rest of your day.